Hello everyone, and welcome to my presentation for MLCB 2025. My name is Mu Qiao. Today, I'm thrilled to introduce OT-Mesh, a fast and accurate framework for uncovering the evolutionary connections between cell types across species. The explosion of single-cell data has given us an unprecedented view of life diversity, but it also presents a fundamental challenge: how to identify cell type homologies between species. For example, looking at these clusters, how do we know which mouse cell type corresponds to the blue cell type in macaque? To solve this, several approaches have been developed, but each comes with certain trade-offs. Reference-based methods, like XGBoost, are supervised, which forces one species to be the reference and creates an inherent asymmetry and bias. Projection-based methods, like Harmony, are often slow and operate on single cells, which can obscure the direct type-to-type relationships we want to find. Even recent optimal transport methods, like RefCM, can be limited by the high computational cost of calculating exact Earth movers distances. This brings us to the key question that motivated our work: how can we find cell type matches that are simultaneously accurate, interpretable, and scalable? Our solution is OT-Mesh, a scalable and interpretable optimal transport framework. Here is how it works. We start by representing each cell type by its average gene expression, or centroid. Next, we build a cost matrix measuring the dissimilarity between every pair of cell types. Then we apply an efficient optimal transport algorithm called sinkhorn. This initially produces a diffuse or blurry mapping that is hard to interpret. And here is a key step. We apply a refinement process called MESH, which stands for Minimized Entropy of Sinkhorn. This procedure iteratively updates the costs to actively promote sparsity, transforming that diffuse matrix into a sharp, interpretable set of high confidence matches. Critically, the MESH procedure discovers these sparse mappings automatically without needing any prior constraint. So how does it perform? We tested it on large synthetic datasets with up to 500 cell types. In panel A, we show that in terms of speed, OT-Mesh is the blue line at the bottom. It is incredibly fast and therefore scalable, while other methods become much slower except the standard Sinkhorn OT. However, as shown in panel B, the trade-off of standard Sinkhorn OT is that it has extremely low matching accuracy measured by adjusted RAND index. In contrast, OT-Mesh achieves near perfect performance. The only method that slightly outperforms it is RefCM strict. However, this method was essentially given a cheat sheet. Its hyperparameters were configured to enforce one-to-one mapping that we knew was in the ground truth. When you remove that constraint, as in RefCM flexible, its accuracy drops dramatically. OT-Mesh achieves its high performance without such limits, making it far more practical for real-world discovery, where the ground truth is unknown. More critically, it produces highly sparse and interpretable solutions, indicated by its low solution entropy in panel C. Of course, data isn't always clean, it's noisy, so we tested its robustness to noise level. As you can see, even as we crank up the noise levels, the accuracy of OT-Mesh remains remarkably stable and high, and its solutions stay sparse. These results confirm that OT-Mesh successfully achieves our three goals: near optimal accuracy, sub-second runtime, and remarkable robustness. With this strong performance, we applied OT-Mesh to a complex real-world problem, mapping retinal cell types between the mouse and macaque. First, we look at bipolar cells. Our method not only confirmed previously reported matches, but also proposed this missing matching between macaque DB4 and DB5 to mouse BC type 5. The initial report has linked DB5 to rod bipolar cells, which was unlikely, given DB5 is a cone bipolar cell in macaque. Our proposal is more biological plausible, as DB4 and DB5 align better with mouse BC5, given their similar functions and anatomical structures. This gave us confidence that OT-Mesh works well on real-world biological data. Then we move to retinal ganglion cells. This is where it got really exciting. Besides confirming known matches between mouse alpha retinal ganglion cells and macaque midget and parasol cells, OT-MESH identifies a strong and specific correspondence between a mouse on-direction selective cell, which is the C10 cell type here, and the macaque cell type FRGC12. This was thrilling as the existence of on-direction selective retinal ganglion cells was not clear in primates. Amazingly, this exact relationship was independently discovered and experimentally validated by Wang in a Nature paper, providing powerful external validation of our method's predictive power. This shows OT-MESH can reveal both conserved and novel cell type relationships. In conclusion, OT-MESH offers a framework for cross-species cell type mapping that is symmetric and accuracy, avoiding reference bias, efficient and scalable to modern large-scale datasets, and interpretable, producing sparse, meaningful mappings. We are excited about future directions like extending this to handle more divergent species and integrating multiple data types like morphology and physiology. Thank you for your attention. This code is available on GitHub, and I'm happy to answer any questions.